Hello. Today we're going to talk about the fundamental theorem of calculus. Specifically, we're going to prove it. Just before we jump into the proof, let us think about what this thing is telling us. It's really quite remarkable. In the same way that the functions that you're used to, say for example f of x equals x squared, and inverse function f to the minus 1 of x equals square root x, in exactly the same way that these two functions work where one undoes the other, such that if I had a box that did x squared and then I had another box that did square root x, and I took and I put in here any positive number, let us say for example 5, then it would go through the first box, it would get squared, I would get 25, it would go into the second box, I would take the square root, and I would get back out what I started from. So I started the procedure with 5, and after I had done both my functions, one after the other, I end up with the same thing that I started with. So that is because the function f, being this x squared, and the function square root x being the inverse function to x squared. In exactly that same way, we have two different operations that we can perform that we have seen. We have the operation of integration and the operation of differentiation. And they are related to one another in the same manner. So it is the case that if I was to do something else here, take a box, and this box would perform integration, and then I would take the output of that into another box whose job would be to perform differentiation, that at the end of the day, if I was to take a function here, I would integrate the function, then take the derivative of the function, I would return back to the function that I started with. This is a remarkable fact. That is part one of the fundamental theorem of calculus. Part two of the fundamental theorem of calculus tells us that if we are in the situation where we are attempting to find the area under a curve, imagine I'm trying to find the area under this curve. So far we've seen how to do this using a limit of a sum, the Riemann sum. If I'm able to take the function describing this equation, if I'm able to find an antiderivative, so let me then say what I mean there. If I'm able to find a function f such that f prime of x equals f of x, that means that capital F of x is an antiderivative of f of x. If that is the case, that I can do that, then this area that I have shown here underneath my curve, that area is going to be equal to f, capital F, evaluated at the right endpoint minus capital F evaluated at the left-hand endpoint, which the two endpoints here determining the interval on which we want to find the area under the curve f of x. So remarkably, given an antiderivative, I only have to know information about that antiderivative at the two endpoints, and no matter what the shape of my curve is, those two evaluations give me exactly the area under the curve. So we're going to state this now more formally, and then we're going to prove that this is indeed the case. Since this was prepared for students in my class in Math152 in the spring of 2018, you will recognize that you are in a course called Calculus 2. This is the fundamental theorem of calculus. That word, fundamental, is a major clue that this is a theorem of major importance in calculus. We are studying calculus. You must be able to state this theorem. It's important that you understand both parts of it and that you can state the theorem. Okay, so let us do that. Let us state the theorem. It comes in two parts. Part one. Part one. What does part one say? Let us take a look at the conditions that we have to satisfy before the theorem applies. This is always really important to understand under what hypotheses is the theorem true. Okay, so in this case, the theorem is true if f is continuous. So we need to be talking about a continuous function. So if x is continuous, and f is going to be continuous on a closed interval a, b. So that is our hypothesis. We have a continuous function on a closed interval. Then the function defined by, now we're going to define a new function. Here's our new function, g of x. That is, we're defining this function, and it is going to be defined as the integral from a to x of f of t dt. So I'm going to take that continuous function that I have, and I am going to define a new function to be the integral from a to x of my continuous function. Okay, what does this mean? This means in the same way that if I had some other function, let's just assume I have some other function, let me say something like this, m of x equals x squared, then m of 2 would of course be 2 squared. I would substitute in the 2 for the x. In the case that I have here, g of x is defined as that integral, meaning that, for example, g of 2 would be the integral from a to 2 of f of t dt. This function operates in the same manner as functions that you're used to. If you want to evaluate g of x at any number x, you simply substitute in the number for x wherever you see the x. Okay, so we've defined this function. What can we say about this function? What is our theorem going to tell us about this function? Well, it's going to say that g of x, so here are the things that we are going to be able to say about this new function that we've defined, g of x. Well, first of all, g of x is defined on an interval, on the same interval that f of x is defined on. So let us make note of that. So x is going to be allowed to vary within the range between a and b. So this new function, g of x, is 1, continuous on the closed interval ab. And that's point 1. So however this function, whichever evaluations we get, if we were to draw a picture of this new function g of x, we would find that, roughly speaking, we could draw it without lifting up our pencil. Okay, what else is g of x? G of x is differentiable on the open interval ab. Okay, so this means that, loosely speaking, g of x is a smoothish looking function. It doesn't have any corners or doesn't zoom off to infinity. Nothing sort of funny happens. It's a nice looking function. It is at some level smooth. Okay, so that's the second point. Third point, what else? And this is really the one that we're going to use all of the time when we're solving problems. It is the case that if I take the derivative of g of x, then that will be equal to f of x. This is that first example that I gave with the boxes to say, if you take an integral and then you take of a function and then you take the derivative of the resulting function, you get back to where you started from. Okay, so that is a statement. These last 3 points are the conclusions of the theorem. So we had the hypothesis. We start with a continuous function on a closed interval. Then we define a function, and then we are going to prove these 3 conclusions here. That the function that we chose to define is continuous, differentiable, and that the derivative of that function, g prime of x, equals f of x. This portion here, we could state this here in Leibniz notation. Okay. That would look like this. The derivative with respect to x of the integral from a to x of the function f of t dt equals f of x. All right, so how are we going to go about doing this? Well, the first thing we're going to do is let us consider x and x plus h. So these are 2 numbers, and they are going to be in the interval, in the open interval AB. So all I've done is said, okay, let's consider the interval that we've defined our function on, let us pick two numbers in that interval. All right, so I have this function. Let me evaluate my function at these 2 points. So I'm going to evaluate my function g at x plus h. I'm going to evaluate my function at x, and I am going to divide that whole thing by h. So right away you should be thinking to yourself, my goodness, that looks like these heading towards the definition of the derivative. If that's what's come into your mind, you are indeed correct. I am trying to set up so that I can figure out what the derivative of g is, because I really want to show that the derivative of g is in fact f of x. So I'm going to set myself up to make a computation here so that I can figure out what is the derivative of g of x. Okay, so what have I got here? That is going to be that h there. I'm just going to have that. I have to have that on this side. And then let me think about it. What is g of x plus h? Here's what g of x plus h is. It is the integral from a to x plus h of f of t dt. That's because we know what g of x is. G of x is the integral from a to x. So the g of x plus h is the integral from a to x plus h. This is just the definition of, this is how we decided to define g of x. And then g of x, we have the definition. Here it is, the integral from a to x of f of t dt. Okay, so I've replaced g of x and g of x plus h with their definition that we have in the theorem. There it is. Okay, what am I going to do next? Well, I would like to possibly simplify this a little bit, and in particular I'm looking at this piece here, this integral right here, and I am recalling. So now what is the fact I'm going to use in this next step? Let me write out the fact that I'm going to use. I'm recalling that the integral from a to c of f of x dx is equal, well, actually let me do it this way. The integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. So loosely speaking, this is something we actually covered recently in class, but let me just draw a quick picture, motivate this geometrically. It's true in general, but if we were in a situation like this, this was our a, this was our b, and here we have some number c like that, what I am saying is this area plus this area is the total area under the curve. That's what this fact is telling me. Okay, so I'm going to be able to use this fact that I'm recalling to split this integral here into two pieces. I'm going to do that right now. Here goes. So I'm leaving the left-hand side alone. G of x plus h minus g of x all over h then is equal to the 1 over h. And now I'm splitting that integral into two, and I am getting this thing here, the integral from a to x of f of t dt plus the integral, I have to shuffle my paper up a bit here, the integral from x plus, let me get this right, sorry, x to x plus h of f of t dt. That's this integral here divided into two right here, and then I'm going to just recopy this one here down. So that becomes minus the integral from a to x of f of t dt. Okay, so I've now got a definition of what this ratio is. This ratio right here, g of x plus h minus g of x over h, is equal to these three integrals. And you can see that this one and this one are the same, so they cancel one another out. So I have now ended up here with a statement of this fact here. G of x plus h minus g of x all over h is 1 over h times the integral from x to x plus h of f of t dt. I'm going to label this guy 1. I may refer back to that as equation number 1. Okay, so I've got a statement that I can use here, and where I'm going with this, I'm looking at this and thinking, wow, if I took the limit as h goes to 0 on here, then I would have, in fact, g prime of h. You recall the definition of the derivative from Calculus 1. Okay, so now I'm going to, because I'm going to start to deal with some inequalities here, I'm going to start by considering values of h greater than 0. The exact same argument is going to follow for h less than 0. We have to do them separately though. We know that f is continuous. Okay, so let me write this down so we're clear. Since f is continuous on this interval x plus h, because f is continuous on the whole interval ab, and going between x and x plus h, we are in the interval ab. So f is continuous there. So I am now going to employ another theorem from Calculus 1. We have a continuous function on a closed interval. So that means there exist numbers. There exist numbers. I'm going to call them u and v. U and v. Okay, so there's two numbers that exist that are in this interval, x plus h, such that f of u equals m and f of v equals m. Okay, so I'm going to be able to evaluate my function. It's a continuous function. I can evaluate it at u and v, and I get these numbers. And I'm specifically going to have chosen u and v such that these two numbers, where m, little m, is the absolute minimum, value of f, and the capital M is the absolute maximum. What theorem is this? All right. Since there's not an audience here, I will simply state this for you. That is the extreme value theorem. I'm going to give a little aside here, a graphical example of this so that you recall what this is. This is a powerful theorem. It basically saying, here if I've got a function, here it is. I don't know, it looks something, any function that you want, a continuous function like this on a closed interval. And it is telling me that somewhere for this example, somewhere, I've now called this v, somewhere it obtains its biggest value. There it is, capital M. And somewhere else, it obtains its minimum value. In this case, that's right here, little m. So this one would be my u. So it's just telling me that if I have a continuous function, it has an absolute maximum somewhere and an absolute minimum somewhere else. So I've identified the x and the y values of the absolute maximum and minimum points. And I've mislabeled this. This is a u. Okay, so f of u equals m is the minimum, and f of v, which equals capital M, is the maximum. Okay, so I'm now in a situation where I have my function, f of x. It is greater than or equal to little m, and it is less than or equal to capital M. That is when x is greater than or equal to a, or less than or equal to b. What does that mean? Well, we've also seen this. That means that for a function that looks like this, look, let me take a shade in the area here. Okay, so I'm going to shade in the area under this curve. And I'm then going to imagine that I take the minimum value like this, and I look at the area of the rectangle formed from my minimum value and across my full interval from a to b. This number here, actually in the drawing I've chosen, a and u are equal. They do not have to be. And then this number here is b, which is not equal to v. Typically speaking, they won't, but of course, as you recall with the extreme value theorem, an absolute minimum or absolute maximum can occur at an endpoint. Okay, so I've got the idea that the area under my function is going to be for sure bigger than the area under the rectangle when I choose my rectangle height to be the minimum value. What does that look like in symbols? The area under my function, f of x dx, is for sure going to be bigger than or equal to the area of the rectangle whose height is the minimum value of the function. There is the height, and the width of that rectangle is b minus a. Okay, so I have now a bound, a lower bound on my integral from a to b. Similarly, I could imagine this large rectangle formed by taking the maximum value of the function. There it is, the maximum value of the function. Of course, once I've shaded this in, you're not going to see the function at all. So now I'm thinking to myself, let me consider this area here. Clearly, that is more area than what was under the function. So by the similar argument of the size of that rectangle, this is going to be less than or equal to capital M times b minus a. Okay. So now I've got a bound on the area of my function from a to b. Now I'm going to take a look at this integral right here, the one I've set up earlier, and I'm quite interested in. That is this integral from x to x plus h of f of t dt. Okay? And I'm going to then, using this argument about the area here, I'm going to say, well, this has to be less than or equal to m times h. And that is because x plus h minus x is equal to h. And similarly, it's going to be greater than or equal to the minimum value of my function times h. Okay. So now I've got a upper and lower bound on that integral. The minimum value of my function m occurs at u. The maximum value of my function, capital M, occurs at x equals v. So I'm going to replace those two in this statement that I've just made. That will be then f of u times h. That is because f of u is little m. That will be less than or equal to the integral from x to x plus h of f of t dt. And that will be less than or equal to f of v times h, because f of v is capital M. I'm going to label this 2, so I can refer back to it if necessary. Now, I'm going to use 1. Use 1. Okay? That was the equation I labeled earlier. I'm going to use 1 because I know what this is. In fact, that's what equation 1 tells me, that this integral is in fact the g of x plus h. Let me write that down. I'm using 1 right here to say that this integral here is g of x plus h minus g of x over h. You showed that earlier. And then that is going to be greater than or equal to f of u, and less than or equal to f of v. Okay, I slightly lied here to you. I'm going to fix this actually. Let me just go back and lie. 1, I should have moved the h. So this statement is true statement. 2 is a true statement. But what I'd actually like to do is divide through everything by h. Remember that here h is greater than 0, so this will not change the inequalities. But in order for me to do this replacement properly, let me do this here. Okay, I'm simply dividing through by h. So I want to express it in this manner. F of u is less than or equal to 1 over h times this, which indeed that allows me to use the 1 that I said and replace that integral here. Okay. I'm happy now. I'm now going to consider, now let h go to 0. It's getting exciting here because once I'm letting h go to 0, this thing here is going to become g prime of x. And I'm trying to figure out what is g prime of x. So I'm going to let h go to 0. Now I have to consider what happens when I let h go to 0. What does f of u become? And what does f of v become? So let's think about that. I'm in this situation where I am letting h go to 0. So h is going to be going to 0. And I'm thinking to myself, what does that mean so what happens to f of u and f of v? Okay. Let us think about that. The limit as h goes to 0 of f of u, that is going to be equal to the limit as u goes to x of f of u. Why is that? Well, okay, so we're here then, h is going to 0, and I'm asking what happens to f of u and f of v as h goes to 0. So I'm thinking, what is the limit as h goes to 0 of f of u? I'm saying that that's the limit as u goes to x of f of u, and that is equal to f of x. Why? Well, we know that u and v are absolute points where the absolute minimum and maximum occur, and we know that they're in the interval u, v are in the interval x plus h. So when h goes to 0, there's only going to be one number left in that interval, and that is going to be x. So similarly, the limit as h goes to 0 of f of v is the limit as v goes to x of f of v, and that is also f of x. Okay, so we're basically shrinking down our interval, and both u and v are becoming x. And as I indicated on the equation earlier, I'm going to restate, from the definition of the derivative, the limit as h goes to 0 of g of x plus h minus g of x over h is g prime at x. That's the definition of the derivative. Definition of the derivative. Okay. All right. What do we have here? We have here f of x less than or equal to g prime of x less than or equal to f of x. This is written out possibly maybe a little bit more carelessly than I should, but that is what we have showed. The limit is on both sides approaches f of x. So this is as h goes to 0. The number in the center is g prime at x, and then we have the two endpoints. And as you can see, the two endpoints are equal. This one limit is f of x. This limit is f of x. Another theorem from Calculus 1, the Squeeze Theorem. Therefore, by the Squeeze Theorem, so if we have a situation where we have some function doing some funky stuff like this, and we manage to find that we have a function that comes like this, that we can find its limit, and the other function comes up here, and we can find that at some point both the upper bound function and the lower bound function approach some number, then the function in the middle, that is squished in the middle, must also approach that number. So that's what we're using here, the Squeeze Theorem. And then we're done. Check that out. We have just showed that then g prime of x is equal to f of x. That is what we wanted to show. The most important part that we're going to use in terms of the three things that we are talked about, the conclusions of our fundamental theorem of calculus. that the function that we defined is continuous, differentiable, and its derivative is f of x. So it's differentiable because we found its derivative. Differentiable functions are continuous. So we are now finished with all three parts that we wanted to say. So this is the important conclusion right here, and we've showed that part one of the fundamental theorem of calculus is true. Okay, let me just restate it in the Leibniz notation below so we see exactly what it is that we've shown. The derivative of the integral from a to x of f of t dt is equal to f of x. Remarkable result. Okay, that is part one. Part two is shorter to show. Oh, actually, there is something I did not show here. I glossed over, and I would actually like to ask you to do this yourself. But I went through this whole procedure from the time I started to introduce the inequalities with h greater than 0. So far we have seen truth. Let me even write that. Truth for h greater than 0. So in order to be completely rigorous, we should show the same thing happens when h is less than 0. This just actually amounts to setting up the inequalities in a different order. Let me, as an aside, just get you started on that. I recommend you actually just go through this and say to yourself, okay, I'm going to put this away aside for a sec, stop the video, whatever you want to do, and put h less than 0 and attempt to write the whole thing out yourself, and then make sure that you can draw the same conclusion using the same theorem. So for the h less than 0, we state that f is continuous. I'm getting you started here. Continuous on, and we're here, x plus h x. Okay, we have that. We have the same f of u. F of u is equal to m, and f of v is equal to capital M. That remains the same. And then we have, looking slightly differently when we set up the integral, because h is negative, we have this m times minus h less than or equal to the integral from x plus h to x of f of t dt, and then we have that less than or equal to m times negative h there. Okay, so we have got this h less than 0. We then use the additional fact that the integral from a to b of f of x dx is equal to negative the integral from b to a of f of x dx. Hopefully that'll give you enough to get started. You can go ahead with this, recalling that when h is less than 0 and you divide by h, you must switch the inequalities. Okay, you must switch the direction of the inequalities. Okay. Other than that, it follows directly, and you've done both sides, so then you can make your conclusion. So in this case, I fully did the case for when h is greater than 0. You're going to fill in the details for when h is less than 0. Okay, that lets us get on to part 2. It'll be much quicker. Part 2 is I think in some ways I find it a bit more remarkable, but it follows quickly from part 1. So let us get a statement of what part 2 of the fundamental theorem of calculus is. So this is the second part that you should be able to state. We have the same hypothesis. If f, this is a hypothesis, is continuous on the closed interval AB, that's our hypothesis, then the integral, the definite integral from a to b, so this is going to be a number. We recall that the definite integral always results in a number. The definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is any antiderivative of little f. What does that mean? That is a function such that f prime is f. Okay? All right, let's take a look at how we would prove this. Proof. Well, what did we just prove? Actually, let us take a look at this function. We have just shown this. I'm going to define that same function g of x as the integral from a to x of f of t dt. There's some function g of x defined in this way. We have just proved that g prime of x is equal to f of x. That is, let me abbreviate this way, by the fundamental theorem of calculus, part 1. Okay, so what does that mean? Actually, the derivative of g is equal to f. That means this means g is an antiderivative of f. What does that mean? G is an antiderivative of f. That means g has a that is telling me actually that g is well, actually the fundamental theorem of calculus tells me that as well. G is an antiderivative of f and g is continuous. Okay? Because we showed in part 1 that the function g of x defined by this integral right here is continuous and differentiable. So we have that it is continuous here as well. Now I'm going to say let f be any other antiderivative of f, little f, on the interval AB, closed interval AB. Okay, so I'm now considering any other possibility. And we will now invoke another theorem from Calculus 1. That will be then f of x is equal to g of x plus c. That is, antiderivatives of a function small f of x vary only by a constant. So let me just make a note here of what we're using. This is a corollary of the theorem of this thing here, which you have seen before from Calculus 1. If the derivative is 0 for all x in the interval AB, then f is constant on AB. Okay? So the constant function is the only function which has a derivative of 0. Okay? So now we have g of x is continuous. This is just some number, a constant. That means that f of x is continuous. Okay, we have a continuous function. Now we can take the limit of that function because it's continuous. So we can take the limit and we can say this about it. The limit as x goes to a from the right is going to be equal to the limit as x goes to a from the right of g of x plus c, because that is what capital F of x is. Okay, and that means that by the continuity, that means that big F evaluated at a is g of a plus that constant. Similarly, f of b is equal to g of b plus c. Okay, let us now take a look what happens if I take the difference between these two things. So I've established this fact here. F of a equals g of a plus c. F of b equals g of b plus c. That means that f of b minus f of a is equal to g of b plus c, that's f of b, minus g of a plus c. That is capital F of a. The constants cancel out, and this is equal to g of b minus g of a. So we have that capital F of b minus capital F of a is g of b minus g of a. I'm going to turn to another page and write that fact down again, because we're very close to getting the conclusion here. We are here. We have established the fact that we have f of b minus f of a being equal to g of b minus g of a. There it is. Okay, let's now take a look at both of these guys. What are they? Okay, let's take a look at g of a first. G of a, okay, maybe even before I do that, I will write out what is the definition of the function g of x. G of x is the integral from a to x of f of t dt. That's how we've defined g of x. So what is g of a? Well, g of a is, I take g of x and I substitute in a for x, and I get the integral from a to a of f of t dt. But that is simply 0. I mean, we're now talking about what area is there under the curve when I don't have any interval. So the width I could think of this as maybe perhaps one rectangle of width 0. So there's just a line there, and that line has no area. So that integral is 0. Okay, what is g of b? Well, same thing. We're going to take g of x and we are going to substitute in b. So that'll be the integral from a to b of f of t dt. That's what g of b is. Now I'm going to simply substitute into this thing right here. I'm going to substitute in g of b, that I just figured out what that is, and I'm going to substitute in g of a. So I will have f of b minus f of a is equal to g of b, the integral from a to b of f of t dt, minus the integral from, that's g of b, minus g of a, which is the integral from a to a of f of t dt, which is 0. And we are done. So what's happened here, let me just rewrite. Of course, I don't need the 0 here. I'm going to rewrite this. The integral from a to b of f of t dt is equal to f at b minus f at a, where we started was the fact that f is an antiderivative of little f. And that's it. That's what allows us to evaluate a definite integral by just using the antiderivative at the endpoints, which means we no longer, should we choose not to, we no longer have to set this up as the limit of a Riemann sum, which is of course much more cumbersome than using this. I want you to see the analogous comparison between what happened when you were taking a derivative always using the limit definition, and then a little bit later on we got some more high-powered tools and we could start taking the derivative without having to use the limit definition. In the same way, now we can calculate these definite integrals without having to set up the limit on a Riemann sum. And that is both parts of the fundamental theorem of calculus.